So now let's look at some applications. What's the simplest application? The simplest application, and actually most of the applications come from different interpretation of what the function is. So if you assume that f of t is a position of a particle, right, then does it make sense to integrate that? What's the meaning of the integral of position? Is it? No. Right? So it doesn't make much sense to integrate position. So if you want to apply the first part, you better have something meaningful after you integrate the function. So if I now assume f is velocity of a particle, then the first statement says if I integrate velocity from 0 to some time tau, and then I differentiate the result with respect to that upper limit tau, it will be the velocity back at that time tau. So what's the meaning of this? What is the integral of velocity? Well, that's position, right? Now, what happens if I make the upper limit changing and the lower limit the same? It means that I consider motion from time t equals 0 to some time t equals tau, and I allow that ending time to change. And then I see what happens, right? So the whole integral here is going to be about the result of moving from time equals 0 to time equals tau. And what is it that I'm looking at? I'm looking at position at this time tau. And I'm trying to change that tau. I'm trying to move further by a little bit. And see what the rate of change of that is going to be with respect to tau, with respect to time. Now, what is the rate of change of position with respect to time? Velocity. That's what it is. So that's exactly what the fundamental theorem of calculus says in vector valued version. And the whole argument doesn't depend on whether you do it in a plane or in 3 space or in 4 space. So your particle is moving, and it says that the rate of change of position is exactly velocity. Of course, if you started with velocity initially. And also, if you interpret f as acceleration, then integral of acceleration is velocity, and the rate of change of velocity is acceleration. So there is nothing extremely new about this. Well, the second theorem states essentially the same. Integral of f prime of t dt. So what is that? We'll say if f of t is velocity, then f prime is acceleration. Integral of acceleration from a to b is equal to what? F of b minus f of a. Integral of acceleration is the change of velocity. Well, nothing particularly new. It's just multivariable version of the same stuff you did in Calc 1.